In the last lecture, we promised to cover some material at the very end, but we ran out of time and could not cover that material. So what we're going to do in today's lecture is just to cover the material that we promised to cover at the end of the previous lecture. In that sense, this should be a relatively short lecture. Okay, so what was the material that we promised to cover at the end of the previous lecture, but could not get to it because of time? When we apply the simplex algorithm, the linear programs on which we apply the simplex algorithm were always of the form: all constraints are less than or equal to constraints, and all of our decision variables are restricted to be greater or equal to 0, right? So when we designed the algorithm, when we designed the simplex algorithm, all the linear programs that we solved had less than or equal to constraints, and all decision variables were restricted to be greater or equal to 0. But in general, we may want to solve much more general types of linear programs. So in the linear program that we would like to solve, we may have some constraints less than or equal to, we may have some constraints greater or equal to, we may have some constraints equality constraints. Or in our linear program, we may have some decision variables that are restricted to be greater or equal to 0, they're restricted to be less than or equal to 0, or maybe we can have some decision variables that can both take positive and negative values. For example, a decision variable could represent the spending from a budget. A positive value of that decision variable could be an income into our budget. A negative value for that decision variable could be an expenditure from our budget. And the optimization problem could decide whether we should be doing an income or an expenditure. Okay, so we may be dealing much more general types of linear programs with all less than or equal to, greater than or equal to equality constraints, decision variables that are restricted to be greater or equal to 0, decision variables that are restricted to be less than or equal to 0, or free decision variables that can both take positive and negative values. So now the question we're going to think about is, how can we solve these types of more general linear programs by using the simplex method? And in this lecture, what we're going to see is the following. Give me any linear program of any form with less than or equal to constraints, greater than or equal to constraints, equality constraints, any mixture of these, with decision variables that are restricted to be greater than or equal to 0, less than or equal to 0, with free decision variables, any type of decision variables. Give me any general linear program with any types of constraints, any type of decision variables. I can always convert that linear program where all the constraints are less than or equal to constraints and all the decision variables are greater than or equal to 0. That's what we're going to see. Give me any linear program with any types of constraints and with decision variables greater than or equal to 0, less than or equal to 0, free, whatever it is. I can always convert that linear program into the form where all the constraints are less than or equal to constraints and all the decision variables are restricted to be greater than or equal to 0. In that case, we know how to deal with those kinds of linear programs in our simplex method. So that's the result that we would like to see. Okay, so let's share our screen and get some of those results on paper, get some of those ideas on paper. So let's say linear programs in general form. So far, when we apply the simplex algorithm, we apply the simplex algorithm to linear programs of the form where all the constraints are less than or equal constraints and all the decision variables are non-negative. All decision variables were restricted to be greater than or equal to 0. So far, we applied the simplex method on linear programs of the form, let's say. So let's write a general linear program where all the constraints are less than or equal to constraints and all decision variables are non-negative. So far, we applied the simplex method on linear programs of the form, maximize. Let me take a linear program with n decision variables. So my decision variables are indexed by xj's, objective function coefficient of decision variables, objective function coefficient of decision variable xj is cj. So we're maximizing a cj times xj, added over all j type of a objective function. Let's write a whole bunch of less than or equal to constraints. Let's say the coefficient of the decision variable xj in the ith constraint is aij. Aij times xj is added over all j's. This left-hand side of the ith constraint is less than or equal to bi. And let's say we have m of these constraints, and all of our decision variables are restricted to be non-negative. J is equal to 1 to m. So far we applied simplex algorithm on the linear programs of the form. We're maximizing an objective function with all less than or equal to constraints and with all non-negative decision variables. And the question we're interested in is, How can we deal with linear programs of more general form? Some constraints could be less than or equal to, some constraints could be greater than or equal to, some constraints could be equality constraints, some decision variables could be restricted to be greater than or equal to 0, some decision variables could be restricted to be less than or equal to 0, or some decision variables could be allowed to take both positive and negative values. So how can we deal with linear programs of more general form? And the answer to that is, it turns out any linear program of any general form can always turn into this form, maximizing an objective function subject less than constraints with greater than or equal to 0 decision variables. It turns out any linear program with, let's say, with any type of constraints less than or equal to, greater than or equal to inequality, less than or equal to, greater than or equal to equality. It turns out any linear program with any type of constraint less than or greater than or equal to equality and any type of decision variables greater than or equal to 0, less than or equal to 0, or free can be converted into the form above. Maximizing an objective function, all less than or equal to constraints, all greater or equal to 0 decision variables. Let's see how I can take a general linear program, always convert into this form. Okay? Let's see how we can do that. Maximize an objective function, all less than or equal to constraints with all greater or equal to 0 decision variables. Let's see how we can do that. Observation number 1. If you give me an objective function that I'm minimizing, I can always turn the problem into a maximization problem by maximizing the negative of the objective function. So if I have an objective function that I'm minimizing, equivalently, I can always maximize the negative objective function, negative of this objective function. So minimizing an objective function is equivalent to maximizing the negative of this objective function. So I can always turn a minimization problem into a maximization problem. So that's one. Second, if you give me a constraint that is a greater or equal to constraint, how can I turn into a less than or equal to constraint? Let's say you give me a constraint that is of the form sum of aij times xj's added over all j is greater or equal to bi. This is a greater or equal to constraint. How can I turn this into a less than or equal to constraint? Multiply both sides of this constraint by -1, it's going to turn into a less than or equal to constraint. So I can always turn a greater than or equal to constraint into a less than or equal to constraint by multiplying the constraint by -1. So it's easy to turn a greater or equal to constraint into a less than or equal to constraint. What else? Let's say you give me an equality constraint. Okay. Saying that sum over aij times xj is exactly equal to bi is the same thing as saying that sum over aij times xj is greater or equal to bi and also less than or equal to bi at the same time, right? Saying that this quantity is exactly equal to this quantity is the same thing as saying this quantity should be greater or equal to this quantity and this quantity should be less than or equal to this quantity. So now I can turn an equality constraint, into two inequality constraints. Aij times xj. I can turn an equality constraint into two, I can write an equality constraint equivalently as two inequality constraints. Okay. Like, for example, saying 5 equals 5 is the same thing as saying 5 is less than or equal to 5 and 5 is greater than or equal to 5 at the same time. That's what we're getting at. So if you give me an equality constraint, I can write this as two inequality constraints. If the left-hand side is supposed to be equal to right-hand side, I can express as left should be less than or equal to right-hand side, left should be greater or equal to right-hand side. So these two constraints, they come to this constraint. And of course, if you want to turn this into a less than or equal constraint, you also multiply this thing by -1, this turn into a less than or equal to constraint. Good. So I can express equality constraints as two inequality constraints. What else? Let's imagine that we have a decision variable that is restricted to be less than or equal to 0. Okay? If xg is less than or equal to 0, then minus xg is greater than or equal to 0. So now what that means is I can define a new decision variable, call this yj, and yj is the interpretation of being minus xj. Okay. So in that case, if I'm trying to capture a decision variable that is restricted to be less than or equal to 0, I can define a new decision variable yj that is greater than or equal to 0, and replace all occurrence of xj by minus yj. So now let's say define a new decision variable yj greater than or equal to 0, and replace all occurrences of xj by minus yj. Okay? The idea is if xj is restricted to be less than or equal to 0, then minus xg is going to be greater than or equal to 0. So now we could define a new decision variable yj, which is the interpretation of minus xj. In that case, yj is going to be greater than or equal to 0, and replace all occurrence of xj by minus yj. And let's say the final one, let's say that we have a decision variable xj free that can both take positive and negative values. Okay, let's say we have a decision variable xj free that can both take positive and negative values. The trick over here is that a number, whether it's positive or negative, a number can always be written as a difference of two positive numbers. Let me say it again. The trick over here is that a number, irrespective of whether it's positive or negative, a number can always be written as the difference of two positive numbers. Like for example, I can write 5 as 11 minus 6. 5 can be written as the difference of two positive numbers. Likewise, I can write 4 as, I can write minus 4 as, I can write minus 4 as 2 minus 6. So I can write a number, whether it's positive or negative, as always the difference of two positive numbers. Okay? Good. So if I have a decision variable xj that is free, then we can express xj as difference of two positive decision variables. Let's say xj can be expressed as xj hat minus xj bar, let's say, and xj hat and xj bar are non-negative. So then if I have a decision variable that's free, what we can do is we can define two new decision variables, xj hat and xj bar, that are both greater than or equal to 0, and we replace all occurrence of xj by xj hat minus xj bar. Define two new decision variables, xj hat, xj bar, they're both non-negative, and we replace all occurrences of xj by xj hat minus xj bar. Okay. So if you have a free decision variable, we represent free decision variable as the difference of two positive decision variables. Okay. So now let's do an example to see these ideas in action. Let's take an example where we take a linear program that is of more general form with all kinds of different types of constraints, with all kinds of different types of decision variables, and see how we can convert this linear program into the form where we're maximizing an objective function subject to all less than or equal to 0 constraints and subject with all decision variables that are greater than or equal to 0. Let's see how this works. Here is my example linear program. Let's say we take this linear program. We're minimizing the objective function 5x1 minus 9x2 plus 3x3 plus 4x4 subject to one equality constraint, one greater than or equal to constraint, 2x1 plus 3x3 is greater than or equal to 7, and one less than or equal to constraint, x2 plus 6x4 less than or equal to 4. And our decision variable, the x1 is greater than or equal to 0. Let's say x2 is free. It can take both negative or positive values. So the optimization is going to determine the value of x2. And x3, let's say, is less than or equal to 0, restrict to be negative, and x4 is greater than or equal to 0. So let's take this linear program. Let's take this linear program, convert it into a form where we're maximizing the objective function with all less than or equal to constraints and all greater than or equal to 0 decision variables. Okay, let's do it. Let's keep the objective function as it is for the time being. x1 is greater than or equal to 0, so I don't need to worry about the decision variable x1. x2 is free, which means that I'm going to replace x2 by the difference of two decision variables, x2 hat minus x2 bar. So in the objective function, 5x1 remains as it is, minus 9 times. I'm going to replace all occurrence of x2 by the difference of two non-negative decision variables, x2 hat minus x2 bar. Good. The decision variable x3 is restricted to be less than or equal to 0. So I'm going to replace all occurrence of x3 as a decision with the decision variable minus y3. And x4 is a decision variable that's restricted to be greater than or equal to 0. Keep x4 as it is. Good. So x1 is greater or equal to 0. Here I replace x2 by difference of two non-negative decision variables. x2 hat is greater than or equal to 0. x2 bar is greater than or equal to 0. x3 is less than or equal to 0, so I replace x3 by minus y3, and y3 is greater than or equal to 0. And x4 was already greater than or equal to 0, so we left x4 alone. Okay. Let's do the same thing in the constraints. Let's do the same thing in the constraints. We kept x1 as it is. We replace x2 by the difference of two non-negative decision variables. We replace x2 by x2 hat minus x2 bar plus 5 times x3. We replace x3 by minus y3 right there, plus 2 times x4 was already a greater or equal to 0 decision variable. We left x4 as alone. Good. This is an equals to 9 constraint. So I'm going to write equals to 9 constraint as the left-hand side is less than or equal to 9. And also the same left-hand side is greater or equal to 9. So these two constraints are taking care of this one constraint. The left-hand side is less than or equal to 9. The left-hand side is greater or equal to 9. Great. Let's take care of the second constraint, 2 times. x1 was already a greater or equal to 0 decision variable, so we did not mess with x1. Plus 3 times. We replace x3 by minus y3. Greater or equal to 7. This is my y3. And x2, let's deal with the third constraint. In x2, we replace x2 by the difference of two non-negative decision variables. That is my x2. Plus, we left x4 untouched because it was already a greater than equal to 0 decision variable. This is a less than equal to 4 constraint. Okay. So then to wrap it all up, to turn this linear program into the form where we maximize the objective function, subject to all less than or equal to constraints with decision variables greater than or equal to 0. Let's turn the minimization into a maximization problem. Minimizing this objective is the same as maximizing the negative of this objective. Minimizing this objective is the same as maximizing the negative of this objective. Minimizing this objective is the same as maximizing negative objective. So maximize the negative of this objective, maximize minus 5x1, multiplied by negative, that's going to be a plus 9 x2 hat minus x2 bar. So let's distribute that 9. So multiply that negative 1, that's going to be a plus 9, distributed over 9x2 hat minus 9x2 bar. Again, I have right now is minus 3y3. We're multiplying this by negative 1. It's going to be a 3y3. We're multiplying this by negative 1 minus 4x4. That's the objective function. We turn the objective function from min to max. Let's write this constraint as it is because it's a less than or equal to constraint. That's the form that I like anyway. x1 plus 7 x2 hat minus 7 x2 bar minus 5y3 plus 2x4 is less than or equal to 9. So this is a less than or equal to constraint already. Let's turn this constraint into a less than or equal to constraint by multiplying everything by -1. Minus x1, minus 7 here, minus 7x2 hat. And if I distribute minus 7 over here, it's going to be a plus 7x2 bar. We're multiplying everything by -1, so that's a minus 5, another minus y3, that's going to be a plus y3. Multiplying everything by -1 minus 2x4 is less than or equal to -9. Let's also turn this constraint into a less than or equal to constraint, this constraint over here, by multiplying everything by -1. Minus 2x1, that is a minus 3y3 multiplied by -1 plus 3y3 is less than or equal to -7. And its constraint is already a less than or equal to constraint. Let's write it as it is. x2 hat minus x2 bar plus 6x4 is less than or equal to 4. And all of our decision variables are non-negative. Good. So we took the linear program at the beginning, which had a mix of equality, greater than or equal to, less than or equal to constraints, which had a mix of greater than or equal to 0, free, and less than or equal to 0 type of decision variables. And we convert into a linear program where all of our constraints are less than or equal to constraints. We're maximizing the objective function, and all of decision variables are non-negative. So now this is the kind of linear program that we know how to input into the simplex method and solve. So if I wanted to solve this linear program, first I bring it into this standard form, where all the constraints are less than the constraints and all decision variables are greater than or equal to 0. Then this is the form that I know how to put into the simplex method and solve this linear program through the simplex method. So then the gist of this lecture's discussion is that if you give me any linear program with less than or equal to constraints, greater than or equal to constraints, equality constraints, with minimization objective function, maximization objective function, whatever, with decision variables restricted to be greater than or equal to 0, restricted to be less than or equal to 0, restricted to be free, whatever, if you give me any linear program, I can always turn it into a linear program where we're maximizing the objective function with all less than or equal to constraints and with the decision variables all restricted to be greater or equal to 0. And then you can take that linear program, put it into the simplex method as we've been discussing in the previous past lectures. Okay, good. So this means that we can solve any kind of general linear program by using the simplex method. Bring it into the standard form, less than the constraints, greater or equal to 0 decision variables, and then feed it into the simplex. Okay, good. Let's stop here.